I had to laugh at the screen that Ramon had up on here, or whoever is organizing, whoever's laptop this is. It had this exact same image of the Earth on the desktop, so we've been staring at it for the past few days. And it's great. It's like a beautiful testament to our ability to remotely probe and sense the planet and understand how it operates. And really, we're getting unprecedented new views into the Earth system. But of course, what's missing in this remotely sensed and viewed picture of the Earth is something that can't be easily interrogated through remotely deployed instrumentation, and that is, to borrow the phrase of the USGS, the tapestry of time that's so richly encoded in the geological record of the Earth's surface. And that's beautifully shown in this geological map here. And I'm primarily a stratigrapher and paleobiologist, believe it or not, and I'm principally interested in characterizing this tapestry of time a little better. And as geologists, of course, many of us are used to hearing the standard mantra that goes all the way back to Charles Darwin, that the geological record, this tapestry is tattered and torn and ravaged by geological processes and time, such that the farther we go back in time, the less clear our understanding of the Earth's history and condition becomes, and it's almost impossible to study something like evolution in the geologic record. Or so that was the story told by Charles Darwin. Now, I think our modern perspective is that this is very incorrect, that in fact the geological record does in fact record a very rich record of interacting Earth processes. It provides a very clear documentation of evolution, tectonics, and climate change of very profound kinds over the past 4 billion years. It's also, of course, an important player in shaping the very nature of the Earth that we have today. Think, for example, of the chemical composition of the atmosphere. If it were not for the accumulation of this rock record, we would have a very, very different planet in every way. It's an active participant in shaping the evolution of the Earth system. What Darwin was correct about, however, is that it is a very incomplete quantitative understanding that we have of this upper crust. And our documentation and measurement of it is what is inadequate. Itself it's rather good. So what I've been spending a lot of time doing is trying to quantify and better understand Earth's rock record to get at the history of Earth processes and how the shaping of Earth processes has played out in the very formation of the crustal structures that we have today. So I'm going to tell you about a data set I've put together called Macrostrat. I don't have a lot of time here, and I want to hopefully end on time, maybe even a little early for some questions, and give you a general sense of the approach I take called macrostratigraphy. It's really quite simple. It's basically a chronostratigraphic view of the upper crust that has some desirable quantitative properties, allows us to derive some quantities that are useful for summarizing it. I'll show you some of those in a bit. But the data set itself consists of this sort of tesseration of the continent into these roughly geologically coherent areas, although the spatial boundaries between them are obviously just a tessellation. There's about 1,400 or so control regions in total of the data set. I'm only going to be talking about about 1,000 or so in North America that you can see here today. Within these 1,400 regions are about 3,300 or so lithostratigraphic rock units, basically formations essentially for sediments, for example, plutons for igneous rocks. There's about 7,000 or so gap-bound packages which sort of form the quantitative basis for macrostratigraphy. An important point is that it's pretty comprehensive. Both the surface and the subsurface are included, so that means most known rocks in the upper crust are included in some capacity. And each of those sort of lithostratigraphic rocks has some attributes associated with it, lithology, surface, and thickness, and so forth. It's also integrated with bedrock geology maps for North America, and there's a lot of data at several different scales of resolution there. To borrow the phrase of or borrow the terminology of the EarthScope Cyber Infrastructure Committee and others, these are basically level 2 data. They're summaries of knowledge for regions that are informed by all sorts of primary geological data that are not easily accessible in most cases from this synthesis. So what I'm going to first do is give you just a general sense of what these data look like, and this is an easy way to do that. This is sort of a chronostratigraphic view that forms a very important basis of this data set for something like the basin and range. And each one of those little columns there is just one control region in that little Nevada-Utah area. And each one of the color blocks in those columns corresponds to a lithostratigraphic unit, formations basically. The white areas in this are hiatuses in time, so time intervals at that location that are not represented by any rock whatsoever. And then the colors correspond to basic rock types. And so in the basin and range here, at a glance, you can sort of see the first order geological history that's preserved here. For those of you know the geological history of the region will see many familiar things. The big gap between the blue and yellows and the orange and greens and so forth, that's the Permo-Triassic boundary, the first order shift in the nature of the geologic record in this part of the world, from basically passive margin, more or less, marine sediments to volcanic and igneous and non-marine coarse clastics. So that's sort of the basic view there. But what we're going to do then is I'm going to show you an animation that's going to pull back through the chronostratigraphic architecture of North America. And this will go back and forth a few times here. And you'll see the different just general rock types that are dominant each one of those little polygons for sedimentary, intrusive and extrusive igneous and metamorphic rocks, the protolith age of the metamorphic rocks. And so what you're seeing here is sort of a 4D geologic map as we pull back time increment by time increment the overlying chronostratigraphic overburden that's present at each one of these locations. Here's another. I put this one in here just to remind me to say that these are integrated with surface maps. So this is the same kind of a thing, but instead of seeing the chronostratigraphic view, you're seeing that plus the superimposed surface outcrop that we have available for each one of these time slices. So a lot of the rocks are in the subsurface, of course, of a given age. And this is all great. These are cool animations. And by the way, I put this in here just to remind myself to say that if you like these sorts of things, you can even download an iOS map that I did not make, but that our data powers, that allows you to access the basics for North America here, bedrock geology and stuff like that. You should always know what rocks you're standing on. Did you know we're on injected gneiss? Okay. So these are all great views, but they're very static, of course, in the geographic sense. And we now know, of course, that geography is not constant with time. And we're now exploring, thanks to Mike Gurnis and the Geoplates application that's been rapidly improving in development recently. We're beginning to integrate these different types of paleogeographic models and even plate deformation models with the stratigraphic constraints provided by something like Macrostrat. It's noteworthy to point out that this is accomplished through web services that allow these data sets and these models to operate independently and be developed independently, but still exchange information back and forth very readily. This is a great advantage of this development approach. And here's an example of an animation that shows two things that are rather important. First of all, the shifting paleogeographic context of this sedimentary, or this rock carapace that drapes North America. But also in this particular version of this animation, the grids are actually deforming at plate boundaries as the polygons expand in the case of the basin range, or shrink in other regions where there's net shortening over time. So this just gives you a sense of some of the visualizations that are possible with this, but the real power of the approach of macrostratigraphy is not in its ability to make these animations, although they're cool. It's in its ability to quantitatively summarize a lot of the flashes that you're seeing on these types of animations. So here's just a couple. I'm just going to show you a couple of very simple examples of some of the quantitative summaries that are possible with these types of data. And these are the simplest results possible, really, for this analysis. And that's just simply how much sediment, in this case, is present. Marine sediment is present in each time increment in the Phanerozoic. And so it's the area coverage in each one of those little frames of that animation, if you will. And we learn a lot of important information quantitative information about the history of sedimentation in North America. The first one that's very important that I hope you appreciate just by looking at this is that there's not a really strong long-term trend in the amount of marine sediment in North America, but if there is one, it's a decrease towards the recent. There's way more Cambrian sediment than there is of Cenozoic sediment in North America. Now, this is prima facie evidence, if you stop and think about it, that Darwin's metaphor for the tattered manuscript is false. There's no good quantitative evidence for the hypothesis that the rock record gets worse back through time. If it did, if that were the dominant signal, there would be a trend through time, but it would be in the opposite direction. It would be a decreasing amount through time. Instead, what we see is the dominant signal that's preserved in the marine sedimentary rock record is a production-dominated signal, how much marine sediment was draped on the continent in the first place. Yes, it's been modified by erosion, but the dominant signal is changes in that term, not in the destruction of it. The other thing we learned is that there's a Permo-Triassic minimum. The most dramatic minimum on this, in this data is not the Permo-Triassic, but it's actually the Precambrian-Cambrian boundary. The average stage in the Cambrian has more sediment than the entire Precambrian combined, and that's a step function change at the base of the Cambrian, a very interesting phenomenon. We also learned that there are highs in the Ordovician and Cretaceous that correspond to sea level high stands, which is, say, large areas of continent flooded. Just so, lest you think there is no erosion, the long publicized and much talked about decay in the rock record through time comes only when you mix in non-marine sediments, which is analogous to mixing half-lives of radioisotopes together, all different radioisotopes, and trying to measure the half-life. It doesn't make any sense. It only emerges when you combine the very rapidly cycling terrestrial component of the sedimentary system and try to estimate the cycling of the sedimentary record. It doesn't make any sense. Okay, but we can also do other things like this, like determine modes of variability as a function of time that are not obvious until you quantify things, although they're very obvious just qualitatively in the way the record looks. Of course, Larry Sloss identified tectonic stratigraphic units called sequences, and we now call them Sloss sequences. They show up very quantitatively in the record of North America in a slightly modified form from what Sloss originally described, and it turns out they have a significant 56 million year cyclicity. There's just various ways of testing for that using normal Fourier transform. And of course, the two modes of variability we see in the Phanerozoic sedimentary record of North America is this longer term signal of the M curve, the continental coalescence and breakup cycle that's been widely documented. It shows up very strongly in the sedimentary record. It's the first order source of variance. The second order source of variance is this 56 million year cycle controlled by I don't know what, but it's very strong. Those two together account for most of what we see. This cyclicity shows up in all kinds of things. It shows up in marine fossil diversity. It shows up in strontium 8786. Ultimately probably has a tectonic cause. We don't know what it is. There's a lot of discussion trying to understand what this 60 million year beat is that shows up in many different records that are sensitive to tectonics and other things. Okay, what else can we learn? Well, I'm not sure how the elevation got into my title, but you can learn a lot about the elevation history of a continent by looking at marine sediments. So here's just an anecdotal example. These are all late Jurassic sediments from around the world. They're all shallow marine. We know they started within 100 meters of the geoid, and yet they have elevations that range from 0 on the coast of England to 1,800 meters or so in Argentina. And so what is this variance in the elevation distribution of the modern elevation distribution of ancient shallow marine sediments that we know were tracers dropped on the continents at a geoid position roughly that's equivalent to sea level? What does this distribution of elevations today tell us, if anything? Well, there's several different hypotheses. One hypothesis is, well, we're talking about shallow sea sediments, and we know sea level has varied, right? So perhaps the first order signal in these data is we have some dominant sea level change signals that's drowning and draining the continents and leaving sediments behind, and then superimpose on that as tectonic uplift of local flavors. And so it spreads out the signal, but the first order control is this 200 meter plus so-called Hack curve or M curve or whatever various iterations there have been. That's one hypothesis. Another hypothesis is that signal is small, and what really dominates is tectonics locally. It's all idiosyncratic. Each little region has its each little own history, and each one, therefore, is not really coherent through time, and every little bit has its own idiosyncratic piece, basically. Another hypothesis, however, is that there's systematic temporal variability in these elevation histories for cohorts of marine sediment that were dropped on the planet at approximately the position of the sea level, geoid, and they've been regularly drifting away from that with very well-defined sets of rules. Now, of course, the marine sediments today look like something like this. So here's some Paleozoic carbonates up in the northern Rockies, and they're high elevation, and we know they have some age, but they also have some thickness. So the sediments also record a vertical tectonic motion themselves in the downward direction as well as in the upward direction with their modern elevation. And so here's just, in this case, it's 18 meters per million years in the downward direction before that thing started going in the upward direction, presumably. And so sedimentation rates provide another sort of, long-term sedimentation rates provide another constraint on vertical tectonic motion. And these are the data for North America. Each one of those points is an independently estimated rate of accumulation in each one of those little packages we saw in those animations. And then the red lines are just fitting the measure of central tendency, median and mean, through those distributions. So on median 15.6, on average 35 meters per million years is what the vertical component is recorded by those packages of sediment. The elevations with that diffusion model give exactly the same quantities, a median of about 15 or 16 to up to 36, depending on if you like a normal diffusion or subdiffusive process. So the vertical component of tectonics that's captured both by the thickness of the sediment and their modern day elevations suggests that there's a pretty regular tectonic process governing their vertical history. So there you go, Nathan, elevations. Hope that's okay. Okay, the quantitative, so what's macrostrat good for? So this is where the next thing comes in here. What's it good for? Well, it's a quantitative space-time rock scaffolding that can hold and unite all kinds of different data together. Of course, one of the things about geoscientists is that we have a massive workforce, a massive infrastructure, a massive US array that's very mobile, as it turns out, that's entirely devoted to making observations from rocks, but there's no systematic organization for those data. There's no way currently to aggregate them, to analyze them. There's no common data structure that's so nicely provided by instrumentation because you define what it's going to measure and it does it, whereas geoscientists are much less structured, and that's to our disadvantage. However, the investment in this array is huge. By my calculations, that's roughly $100 million a year, being very generous with how much time is not spent doing things like collecting the data in the first place. And so what we really need, I think, for the next big thing from my perspective as a sedimentary geologist is we really need an infrastructure to get our collective geology act together, to begin defining some pretty simple but structured data sets that can be populated as we go about our business of doing our local science and trying to understand our local problems so that they can contribute to bigger scale questions. To ultimately work up to a dynamic versioned model of the crust that's a working hypothesis, and that we develop an infrastructure that supports the geoscientists as an instrument so that those individual instruments contribute to something like a US array that is really integrated at some level. And of course, that then becomes a framework for integrating, analyzing, and extrapolating those sample-based data of many different types for other types of questions, such as just a couple that were mentioned here today. And of course, the longer-term view is to really couple these geological observations to a fully 4D model of the evolving Earth system that makes predictions in both ways, that couples the interior Earth to the surface geology and provides a framework for really testing hypotheses. Thanks.